Sathi, Professor Pradeep Kumar Das, Professor Susmita Sur Kolay, other distinguished members of the program committee present here, all participants from other institutions, colleagues of BBPIMT, and my dear students. A warm good morning to all of you and welcome to Day 2 of the Conference on Algorithms and Applications, ALAP 2018. On behalf of the organizing committee, Department of Computer Science and Engineering, I would like to mention that the increasing interest in algorithms has kept us focused in organizing such forums over the last few years, starting with seminar on algorithms and applications in 2014, subsequently in 2016, and now with a conference on this same topic. We have indeed been blessed with tremendous eminent academicians and industry experts mentoring us throughout the journey. Yesterday we had a wonderful session conducted by industry experts from Embedded Systems and Robotic Research Lab of TCS and CDAC Kolkata. It was an enlightening and enriching experience for all, I believe. And we continue our journey today with the first invited talk of the session from Professor Susmita Sur Kolay of Indian Statistical Institute, Kolkata. Professor Susmita Sur Kolay is a professor in charge of the Computer and Communication Sciences Division of Indian Statistical Institute, Kolkata. Her research contributions are in the areas of electronic design automation for VLSI Physical Design, fault modeling and testing, synthesis of quantum computers and graph algorithms. She has co-authored several technical papers in leading international journals and refereed conference proceedings, and chapters in Handbook on Algorithms for VLSI Physical Design Automation. She is a fellow of IETE and IEEE and a senior member of IEEE and ACM. Among other awards, she was the recipient of the President of India Gold Medal at IIT Kharagpur and IBM Faculty Award. May I now request Madam to kindly come forward and deliver her invited speech.
Good morning. It's a great pleasure to be in this institute. Thank you very much for inviting me to be part of this conference on algorithms and applications. I'm very happy to see that there's a conference focusing on algorithms and of course applications have no limit. So I've chosen a topic which is, I would say, I'll try to make it introductory. I've tried to make it introductory in nature and as intuitive as possible, because there are different angles to it, and without going into too much technical detail, but there will be a little bit because I want students to also have some exposure of what's behind this. We've been hearing about quantum computing a lot these days, so I thought that this would be a forum, and this being somewhat of a different nature in terms of the algorithms that we are familiar with in computer science. So the morning session is a good time when people are awake, instead of in the afternoon when you might find it even more more technical in a different direction. So. So the agenda today is that, first, what are the basic operations? What is quantum computing about? So it's the first introduction to, brief introduction to quantum computing. I hope everybody can hear me at the back. Yes. And then I'll briefly, with the help of these operations, how you can design algorithms, which would be of use. And of course, these have to be better than what we have, otherwise why would people get interested in these sort of algorithms? So first, what's quantum computing about? Now, you see, the electronic devices that do the computing for us have been doing the computing for us for more than a century now, starting from even analog computing, have been based on electronics. And today all of us have some form of computing, some form of electronic in each of our pockets if you wish. The mobile phones do a lot of computing, even if it is not smartphone. Still, the earlier generations of mobile phones had computing in there. Now these chips, the electronic chips, are getting, although the size of the chip is the same, but the amount of functionality that you can achieve with these chips is increasing, has been increasing, and the number of such computing devices has, at almost a steady rate, more or less doubled every 2 years or so. And so it's basically leveraging the scale of integration of electronic devices. However, we have almost reached the limits of physics of how small things can be. And today, as of in 2018, the chips are such that the transistors are a few multiples of 22 nanometer. 1 nanometer is 10 to the power minus 9 meters. So human hair is much wider than each of these transistors. So you can imagine the, the amount, I mean the small, the dimension, how small it is. So now classical computing has been going on. So it is time to explore what we can do in other directions. And in addition to that, quantum mechanics has been around for a long time, and it turns out that that can support what is known as massive parallelism. Okay? And therefore, it can lead to what is known as exponential speed up over classical computing. So that's what has been leading researchers to come up with quantum algorithms. And one other dimension which is of importance, imagine that in a 3 centimeter by 3 centimeter space, if you have 1 million transistors packed in there and they are switching, that meaning that there is current flowing through them, and they're changing states. Whenever there's a change of state, there is energy involved and there is heat dissipation or power dissipation. So, and moreover, we have been doing this at very high frequency, in the order of gigahertz. So at that high frequency, those many transistors switching, individually they may be consuming or dissipating very small amount of power, but the numbers and the frequency generates a lot of heat and a lot of power dissipation. So low power design is a key mandate in any design of chips today. Now quantum computing has a very unique feature, what is known as reversible. So I'll show a slide what we mean by reversible. Essentially the word is self-explanatory. That is, that given an input, of course you compute an output. But given the output, can you uniquely determine what the input is? So it is almost like time reversal. And there are, analytically it has been shown from Boltzmann physics and all that, if you can design circuits which can give you reversible logic, then the power dissipation is almost negligible. So, and quantum computing or quantum mechanics supports reversibility. So these are two drivers. One is speed up and second is power. So some bit of history. We had the first, formal notion of computing by Alan Turing, and then in the 30s, 1936, so if you take the date of his thesis, and then the first idea of quantum computing was proposed by Richard Feynman in 1982. I was fortunate to be in that lecture at MIT then. And he just brought it up in the sense that a lot of the computing on those days that was done was not enough to simulate quantum physical or quantum chemistry problems, because that required a large amount of compute power. And he mentioned something to the effect that there's a lot of room in the bottom and that should be explored, in the sense that make use of quantum mechanics to do the computing to simulate quantum mechanics. So that was in 1982, and the first result that came about was from David Deutsch in Oxford, where he looked at and proposed quantum circuits and one first quantum algorithm per se, and I'll give you a brief snapshot in a few slides to just demonstrate what kind of power, but it was more like a toy problem if you can think of it as that. And then the world woke up a few years later in 1997 when Peter Shor at MIT showed that you see, you can multiply two integers very quickly. The algorithms to multiply is very simple. But given an integer, to find the factors, that is the inverse process, is not simple in terms of the number of time steps required. And even today, in classical computing, factorization, as it is known, is a difficult problem, computationally expensive problem in terms of time particularly. And moreover, a lot of cryptography, starting from RSA, actually banks on that fact that it's easy to multiply but hard to factorize. Now Peter Shor showed that with quantum algorithm you can actually factorize in polynomial time, which is a super exponential speed up over the classical factorization algorithm. And that's when, and so all of the cryptographers were at stake thinking that cryptography is going to fail. And so many theoretical computer scientists then started focusing on developing quantum algorithms to find out what other problems can be solved much faster, in the sense having more than polynomial speed up in solving them. There are still lots of computational problems for which as of today, right now, no known polynomial time algorithms exist. So this is a bit out of focus. If I can we focus this? Yeah, still a little bit more. It's going in another direction. Yeah. So the figure here is a huge NMR system which was produced in Berkeley, trying to actually implement these quantum algorithms. And of course later on, in 2012, these two physicists were awarded the Nobel Prize in Physics for actually basically implementing quantum the basics or sort of validating that quantum computing is possible. So there's a story that I'll share with you. The day this prize was announced, I was invited to speak at, this was in the US, and there I have been, since I've been also working in how to build quantum computers in a reliable way. So I was asked to speak on that. And I had sent that abstract, and I'd been traveling all day, so when I went to the the place where I was supposed to give the talk, there were a couple of people who said, oh, it's very appropriate that you're going to talk today. Did you see the news today? And I hadn't, because in the US, somehow I didn't have connectivity and so on. And then I got to know that that was the day on which the Nobel Prize for Physics was announced, and these two, this was on the day that this prize was announced, and it was for quantum computing. There were many, there were many people who thought that this is all theory and this is not going to happen. Even today there are some, but there are technologists who are working, and both experimental and theoretical physicists who are working on that. Okay, so a brief snapshot of what is the power, and so the Deutsch's problem, David Deutsch's problem, is this is the summary, and so you're given a classical black box Boolean function. That is, you're not told what the function is. Okay, Boolean function means that it can take binary variable values, and the outputs are also binary variables, either 0 or 1. And you are told that the function, can you tell, so given this, can you tell whether, so suppose I have only one bit, that means there's only one Boolean variable and it can be of value 0 or 1. Okay? So can you tell that whether the value with input 0 and the value with input 1 are equal for the function? So this is known as, so this would be a constant function in that sense. Now, classically what we would do, we would give it the function, we would feed in this value, compute what is the value for, so, and get the value of f of 0, and then again compute for f of 1. So we are actually evaluating the function twice, and then checking whether they are equal. But the question that Deutsch first asked is, can you answer this question by evaluating the function only once? And he showed that yes. Okay, so some people say that this is a toy problem, and I mean, what's the big deal computing once versus computing twice? So this was for one variable, but what happens when you have n variables? So we'll see what happens. Okay. The second thing was Shor's factorization. So here is a chart that you can see for, if you have 50-digit number, then in classical time it would take 1 second, or maybe today's speeds are even better with multiple cores and all that, you can do better perhaps. But with quantum computing it takes quite a bit of time, and you'll see why it would take time. But as the size grows, so you have a large number with 2000 digits, and that's what you would need for cryptography, not so as simple as this. With classical time, we won't see, I don't know whether anybody would see the answer, but with quantum, you can get the answer in your lifetime, in a year, in less than a year. Another important application came around, and this was done by an Indian scientist, Rover. And so I'll talk about this very briefly to just illustrate what is the idea behind designing such quantum algorithm. And of course, the main thrust was to come up with efficient simulation machinery. Recent spurt has been for all kinds of problems, and also we won't have time to talk about them. But this is more to making the younger researchers here interested to find out more about this, because there's a lot to do in this area. So, just a brief recap of quantum mechanics. So the traditional view, traditional physics view is at the atomic scale, whereas in the quantum computing view is that you have a computational model. In the classical view, we had more or less Boolean values, which is 0 or 1, which is discrete. But here we deal with some complex numbers, and because there's the quantum mechanical state. And in the traditional physics view of quantum mechanics, you would find it's very complicated with integral signs. But in the quantum computing view, this has been transformed into linear algebra and matrix products, okay, which we know how to do more or less efficiently. So that's why people were pessimistic, but now with Shor's factoring algorithm, people think that we really can achieve a lot with quantum computing. So the model is that, suppose the computer has n bits of memory. In the classical case, if n was 2, that is 2 bits of memory, you could store 4 different pieces of information, okay, because there are 4 possibilities. In a random case, what happens is that if you have n bits of memory, there are 2 to the n possibilities, and the probabilities that what is the exact value would be some value in this range of 0 to 1. And it may be that the probability that it is existing in having this value is 0.2, having this value is 0.2, and so on, and this should add up to 1 because it should have one of the 4 values and nothing else. Okay? So this is again in the classical domain. But in the quantum case, what happens is simultaneously it can exist with different probabilities. Okay? So this is where the parallelism can be exploited. Instead of, so if you have 2 to the n possibilities, if you want to evaluate a Boolean variable of n variables, you would have to actually compute the function for 2 to the n times. But here you can do that in one shot, okay, because it can exist in all the 2 to the n states. Here there are 2 to the n states here, there are 2 to the n states here. There's no difference about that. But here at one point of time, exactly one of the 2 to the n is possible. But here all 2 to the n in parallel is possible. That is the major difference, with of course some probability associated. And so what happens is at the end of the computation with all the 2 to the n, when your algorithm is designed in such a way that when you finally do the measurement in the classical domain, the value corresponding to the state, the state corresponding to the correct output value would have the highest probability, and therefore when you measure, that is the state in which you will find. So the purpose of designing the algorithm is to start with the input states and process them iteratively so that the correct value, the state corresponding to the correct output value has the highest probability, and therefore when you measure you get the correct output value. Okay? So the basic unit of information, instead of bit, it's called a qubit. And how do you implement a basic unit of information? These are basically physical implements. It could be the spin state of an electron, it could be the polarization state of a photon, because the spin state could be up or down, so depending on that it would be 0 state or 1 state. And if it is somewhere in between, so that means it's a combination of both simultaneously. Similarly for photon. And the notation is as follows, it's known as the Keck notation. So the 0 state could be the up direction and the 1 state could be the down direction for the electron and so on. Now comes instead of the integrals, now comes the nice discrete matrix notation. So the 0 state is often, conventionally in quantum computing is denoted by this vector, 1 and 0. And so the first column, in the column vector, the first row corresponds to the fact that whether the probability for it being in the 0 state. So if it is a 0 state, of course the 1 is here, and this corresponds to 1 state, so therefore it is 1 over here for 1 state. Now it could be somewhere in between, so then you will have less than 1 value here, less than 1 value here, but because it's a probability, you take the square and add the amplitude, so the square of it is proportional. So this comes from quantum mechanics, should add up to 1. Okay? So for example, if you have a 2-qubit system, you would have, you could have something like this. Okay, so these are the 4 states with these probabilities. You could even have complex values as amplitudes, and then the probability that you get, if you add up, you would find that it comes to 1. Okay, so now the state when you measure will collapse. Although internally it might be in a number of states simultaneously, but a measurement is an interaction with the environment outside, so it would collapse to one of the values. So that's what I was mentioning. So these are the 4 possible states are there, but one of them has 0 probability, and the remaining 3, one has probability half, the 0 state has probability half because it's square of this, 1 0 has probability 1/4, 1 1 has probability 1/4, they add up to 1, and the 0 1 state has 0 probability. So you can have different combinations. Okay. Now the matrix happens to be, from physics you can show that it is what is known as a unitary matrix. Okay. And so therefore multiplication and all that holds. So what is unitary matrix? Quickly. So if you have a matrix U, remember the conjugate, which is basically the complex conjugate, whenever you have a complex number, you take the negative of it, and that is multiplied by the imaginary number I, whatever you get is the complex conjugate. So if this is the matrix U, its complex conjugate would be, you multiply by I these values, and so you take the real values remain as it is, and this is what you get as the complex conjugate. And then you take the transpose. Remember transpose of a matrix, you actually swap between Aij, the entry in the jth column of ith row goes to the entry in the jth row of the ith columns. Okay, so this is what you get. Now, if a matrix is the original matrix was unitary, then for any unitary matrix, if you multiply the original matrix with its complex, its conjugate transpose, you will always get the identity transpose, identity matrix. That is the probability property of unitary matrices, which holds for quantum computing, and this is actually the key for reversibility also. Okay. So suppose I have. So what are the? So therefore, any operation that I will talk of in quantum algorithm will be represented as a unitary matrix, and then the state is represented as a vector. So if you are applying an operation on a state, that is the input would be a state, then you would get another vector which is the output state. Okay, that is how the operation goes on. Okay, so these are the matrix representation. So even with our classical operations, we can have these sort of representations. So let's take the AND function. Remember the digital logic AND function? It's 1 only when both inputs are 1 and it's 0 otherwise. So the way we represent it is that there are 2 inputs, so therefore there are 4 possible states, input states, right? The combinations are 0 0 or 0 1 or 1 1 0 or 1 1. Okay? There is only one output, so there are 2 possible outputs, so that's what you write over here. These are the possible output vectors, these are the possible input vectors. And this matrix is basically an incidence matrix. So you see that for these 3 inputs, the first row entry is 1 in the first, in these 3 columns for the first row, which means that if the inputs are one of these 3, then the output will be 0. And if the inputs are 1 1, then the output will be 1. So wherever, so the entry here is 1 if the input combination gives the corresponding output combination. So that's the representation for any matrix representation of any operation, and this is for classical operation of AND. So it's just a different way of representing a classical operation in a matrix format. In quantum computing also the same happens. Now coming back to reversibility, this is a very apt example over here. You find that if you are told that the output is 1, you know uniquely that the input is 1 1. But if you are told the output is 0, it could be any of these 3 inputs. So you don't know, you cannot say what the output is. So if that is the case, then this function AND is not reversible, it's irreversible. But consider not. Okay? So if the output is 0, you know for sure that the input is 1. If the output is 1, you know for sure that the input is 0. So for all values of output, you can uniquely come back and tell us what the input is. So not is reversible, but AND or most of the classical Boolean logic operations, which are 2 qubit, is irreversible. They are irreversible. Now for reversibility, you would have, what you need is same number of inputs and same number of outputs. Okay, because then what you would have, that the output is basically a unique permutation of the input. Only then can you uniquely determine what the input was given the output. So if that is the case, then the operation matrix would have the same number of rows as columns. It should be a square matrix, and if you have an n variable operation, it would have 2 to the n. So if you have n bit or n variable Boolean operation, If you want a reversible function for it, then you would need, since there are 2 to the n possible inputs, input values, and you would also have 2 to the n possible output values, because now your outputs have to have n bits to be uniquely able to determine what the input value is. So it will always be a square matrix, and moreover for quantum computing, all these matrices will be unitary. Okay? So this is the state 0, 0, this is the state, this is single qubit operation. The classical NOT operation you would have as, the 0, as I showed you, is represented like this, and the 1 is represented by this column vector. Sorry. And the NOT operation is represented by this matrix. Why? Because if it is 0, then the output is 1, so that's why you have a 1 in this column. And if the input is 1, then you have a, in the 0, the output is 0, so you have a 1 over here. So this is how you determine what it is, and it is a unitary matrix. Okay? So I already talked about this. Okay? Hadamard, a French mathematician, actually proposed such a unitary matrix, which is called the Hadamard matrix. And you will notice that if you apply the Hadamard matrix on the 0 state, you will find equal probability. It distributes, or what is known as superposes, the two possible. So you started with a pure 0 with the Hadamard operator on it. What you would get is a combination, or a linear combination of both states possible, which is Hadamard to get back to the unique proper output value that you want. Okay. What about 2 qubits? If there are 2 qubits, there are 4 possible inputs, 4 possible outputs, and so this is a very important, this is called a controlled NOT. So behaviorally what happens is, this is known as the control line. So whenever the control line is 0, whatever comes passes through. Whenever the control line is 1, then whatever is over in the target line, it gets, the NOT operation happens. So basically the NOT operation happens, but it is in a controlled fashion depending on the value of the control line. Okay? So if you look at this, you find that the first digit, the first bit here is for the control line. If it is 1, then what happens is you get a 1 here, so the target line gets flipped and you get a 1, 1. So 1, 0 in the input becomes 1, 1, and if it is 1, 1, it becomes 1, 0 because the second bit gets flipped. So the actual operation you're getting is, on the second line is an XOR operation between the first two. So depending on which is the target line, you can have XOR down or XOR up. Okay? And so this notion can be generalized to any function that you have. You can have a what is known as a controlled operation. Okay? And this is used. So there are various primitives. I won't go into much details about them. Okay, but these are, and then so far we've been looking at basically the ones that we saw were only 1, 0. So how different is it from classical? But because you can allow complex numbers, you see that you also allow values with imaginary numbers or complex numbers. So these are known as rotation over, so there's this big saying what is known as a phase. Okay? So you can do a lot of things over here, and there are some equivalences between all these primitives. Then those were 1 qubit primitives, these are 2 qubit primitives. So now one important thing is these are single operations. Now let us go on to build on them. So suppose I have one operation here and another operation here, then the total operation that you get, so for this input, first you apply the matrix corresponding to this operator, you get a column vector for the next state, and then again you apply the unitary matrix corresponding to this operation, and then that's what you get. So essentially what you're having is the matrix product of the operator of this product, the matrix corresponding to this operator, times the matrix corresponding to this operator. That is how you will evaluate. Okay? So therefore, when you build something, even if you don't have a quantum computer, if you want to simulate it, what you would need is very efficient methods of multiplying, matrix multiplication. And very soon, this is just for 2 qubits. You would have 2 to the n by 2 to the n squared. Okay? So these are what are in series. The operations are in series. Now, there could be also, okay, I'll skip this. Okay. There could be also what is known as in parallel. Okay. So there, what happens is what is known as the Kronecker product. So if that happens, then with this 0, this whole matrix is multiplied, and so you get all zeros here. Then with this one, you multiply all 4, and you get this submatrix here. Okay. And then with this one again, you get this submatrix. So essentially, what is happening? You were multiplying 2 matrices, 2 square matrices. You're getting another square matrix, but the dimensions of this matrix has increased. So if this was 2 to the n by 2 to the n, now this becomes 2 to the twice n by 2 to the twice n. So you can see how it is adding power, but when you get to simulation, it is also an algorithmic challenge. Okay. So now what you have when you are building, when you are actually designing a quantum algorithm, what you have is a sequence or some parallel operations on the inputs. Okay, and this line here, by the way, so these are like the gates that we have in our digital logic circuit, and these lines in digital logic circuit are actually wires through which the electrons or the currents flow. In quantum computer, you will not find any wires. There is no notion of wires. Okay. So what are these lines? This is actually, if this is the input side and that's the output side. So this denotes the time, and you don't physically have gates. You have so in classical computing, what you have electrons going through gates, changing the state of the current value or the voltage value, and then feeding to another gate. So there is a physical thing which is moving. The state is with the gate itself. Okay. Here, the state is with the the value itself. So this operation is with respect to, let's say, if you are using photons, there will be one photon in isolation, because quantum systems need to be isolated to preserve their states. So this would be one photon, this would be another photon. Okay, and to have the effect of this NOT operation, you would apply some fields externally to change the state of that photon, to get what you get over here. And then when you have this, you would apply a different combination of fields to get the effect of this. So it's the same photon in isolation. So if you have n qubits, you will have n photons, and depending on which two or which few qubits are being operated on by a particular type of operation, so for each operation you have a certain field setting that you apply. Okay, so So therefore here there is no current flowing, it's just that the state keeps changing. So this is not a wire through which current flows, but this is the schematic denotation of quantum circuit corresponding to some computation that you want to do. Okay, I'll just skip all this. One thing that, so there is this notion of separable qubits when you can actually have one state expressed as in parallel, but then there is also another notion which is non-separable, and this also gives a lot of power and it is used very often. Okay, so these are local operations. So given a yes/no problem, what you do is apply these local operations and then measure the first qubit. Okay, bounded quantum probabilistic model are the classes of problems which can be solved with a quantum computer, but this doesn't solve all the NP-complete problems or so. Okay. Now for the algorithms, as I said, the Deutsch proposed that algorithm that given a function, can you say whether f of 0 is equal to f of 1? Deutsch extended it, saying that if you are given n plus 1 qubits, and you are also given a promise saying that you don't know the function, you are just told that it's either constant or it's balanced. By balanced I mean among the 2 to the n inputs, for half of them the function has a value 0, for the other half the function has a value 1. So that's why it's called balanced. Now in classically what would you have to do? The question that you want to answer is the given black box function a constant function or a balanced function? Now if the function is neither of the two, of course this is not going to work. So there's a promise that it's one of the two. So that much assumption is done. But even given that these two, classically what would you have to do? You would have to evaluate at least 2 to the n minus 1 times, that is half of these, and then one more. If for so many times it turns out that all of them are the same value, then at this point you can say that it's a constant function. And if after this you find at least two or three different values, then you can say it's balanced. Okay. So classically you will have to do an exponential number of computations. But in quantum, what is done is that you use some sort of a control function over here. I won't get into the details, but I'll just tell you the trick. What happens is converts the amplitude to phase using this. So this is, as you see, Hadamarding to have all the states, all the 2 to the n values here. You start with the one state, 0, 0, all zeros, but you go to, after Hadamard you'll have all 2 to the n states. You apply this in such a way, and then if you can, later on you can go back and work through all this algebra that you have. But basically if the function is constant, then after measurement you will find that it will always be in the 0 state. But if it is balanced, it will never be in the 0 state. Okay? So by just taking the measurement in one quantum operation, you can say whether this is a constant function, the unknown function here. So you have to design this as the black box in an appropriate manner. Okay? So that gives you, shows you that you can have exponential from 2 to the n minus 1 computations you can do with only one computation. So you are doing much fewer computations. Okay? So in the interest of time, these were the two scientists and then the two. So the classical complexity was this, whereas the bounded error classical complexity. Why bounded error? Because there may be an error in measurement, so you will have to repeat that a few times. Okay, so that's the first algorithm which came around. Now the most popular algorithm, Shor's algorithm. So suppose you have this very large number. Okay, so many digits. I mean, it's not 5 digits, 5 integers. It's actually one continuous integer. Okay, with so many digits. And it turns out that it is actually it's not a prime number, it's a product of these two. So the best classical algorithm takes so much time, whereas Shor's quantum algorithm takes 1 minute. And what is the trick? So Shor made use of what is known as the very important result in number theory. That is that if you have, so these are all integers. Okay, so if you have this function, this is the modulo n function, okay, remember? So suppose, let me illustrate quickly with an example because I'm running out of time. So suppose x is 7 and the number n, which you want to factorize, is taken as the modulo. So you choose a number x, which is any number that you want, and you start raising it to various powers, integer powers. So 7 to the power 0 modulo 15, so this is 7 modulo 15, okay. This is 1. Why? Why 7 modulo 15 is 1?
Because 17 plus 3 is 1.
Yes, exactly. And 7 to the power 1 modulo 15 is 7. 7 square modulo 15, 49 modulo 15, again is 45 plus 4. 45 is a multiple of 15, so that's 4. And then when you get to 7 to the power 4, you find that's 1 again. So the important thing is that this function is a periodic function. So that's what Shor made use of. Okay? So the idea is like this. Suppose I want to factorize, this is a very small integer, but I just want to illustrate with this, that if you have a very, so what you have is, this is your n, choose some value x. Now the periodicity that you get is r, because if you raise it to x to the power r, then it goes back to 1. So for example, in the case of when you have 2 and 21, in the previous slide, the periodicity was 4. In this case, the periodicity you find is 6. Now define y to be x raised to the power r by 2 modulo n. So in this case, y is 8. Okay. Now notice, if you have if you take the GCD of 7 and 21, 21 was the n that I want to factorize, then I get 7. And if I take the GCD of 9 and 21, I get 3. And these two are in fact the factors of 21. Okay. So what's the secret? The secret is as follows, that this is y. Okay. Now if I take y square modulo n, of course I would get 1. Okay. So what does that mean? That y square minus 1 is divisible by n. Right? So y plus 1 times y minus 1 would be modulo n 0. So therefore, since y is less than n minus 1 and y minus 1 is less than y plus 1, so you can always take GCD of this with n and this with n, and these, whatever the GCD values, will be the non-trivial factors of n. So this is the key idea which is used in being able to factorize. So the steps here would be to choose a proper integer, and finding the period is what takes time, and that is the portion where quantum operators were used. Finding the GCD we can do fast, okay? And so I'll just skip a few slides over here. Sorry. Okay, so if you choose, so this is the one that I have to factor, of course you need to have it or check whether it's prime, you can do that in polynomial time, check whether it's even number, you can do that in polynomial time, you can even check whether it's an integer power of a prime number. So if it is none, if it is one of these, then you don't use Shor's algorithm. It's like, trying to kill something with, kill a mosquito with a candle, okay? But if it is none of them, then what you do is you start applying this. So you pick some number. So if n was 15, n squared is 225, so you choose a number between this, and you choose a random integer such that which is relatively prime with n. So let's pick 7, and then of course you create these so this is what happens when you try to find the periodicity. I won't go into the details, but basically in the output register we would have these values over here, and then you gradually what is known as, by using Fourier transform, you increase and then try to find the periodicity over there. Okay, so I'll skip this. So essentially you would have superposition of the values where it becomes 1, and then you gradually do the Fourier transform, and essentially at the end what you will have is a value which has the highest probability, and it would be related to the period. of the number that you have in that modular function. Okay? So the factors would be related to the, this is the y plus 1 and y minus 1. So you take the GCD of these that you measure and then you can success that. So you might laugh that to factor 15, why do I do all this? But the point is, this was an illustration, and the first number that you saw, you couldn't have done, I mean, doing this so simply, classically it was not possible. If it fails to produce factor, of course, then you have to repeat this because it might happen because of the Fourier transform, the correct. So you would pick a new value and you would repeat. And it can be shown that it will be only a constant number of times before which you can do that. So the feat here is, in classical machine you would need so many time steps, whereas here you would do it much faster. Okay? Quickly, a very cute idea about unsorted search. This does not give you exponential speed up, but it gives square root of speed up. So suppose you have a list of integers and they're not sorted. If they're sorted, you can apply. What can you apply? To find whether it's something.
Binary search?
Binary search, right? And so you would have, if there are n entries, you would have log n steps. Okay? But if it is not sorted, you would have to, in the worst case, check all of them, order n. Okay? What Lovegrover showed is you can do it in order root n. So I won't go into the details, just the illustration of the very cute idea. So what is done is, suppose I have a list and suppose I'm searching for 2. So the idea is that I want to amplify the value of 2 over here. Okay. Maybe I'll go to the next one. Yeah. So suppose these are indices and I want to find the entry, search for some entry which is an index 2. So the idea is that you build a circuit, you build it in such a way that if it is there, so in this case the target is 2, you negate it. Okay? So this was the target 1 and I negate it, it becomes minus 1. So then this is known as phase change method. And then you take the average of all of them. Okay? So in this case the average is 1.5. Okay? Then you deduct this average value from each of them, and this is the list that you get. Now notice, the target value, the amplitude here is different from this because I specifically changed the smart value which I am targeting. Okay? In this iteration, again you do the same thing, you invert the phase, that means now from all of them remain same except minus 2.5 becomes 2.5. Take the average again and deduct from each, and now you find that if you keep on iterating, what is happening is you started with equal values, but the target value it is increasing and all the others are decreasing. Okay? So that's what we want. This is when you measure, the probability of this state should be very high so that you get the correct answer. So that is what I mean by amplify the target or amplify the state corresponding to the correct output. Of course, you might ask, how many times do we have to do this? If I have to do it n times, then it's as bad. What's the point of all this? So let's skip all this. Sorry. You can actually do this in root n times. Okay, so if there are n elements, you can give the correct answer in square root of n times. Not exponential, but a considerable improvement. Okay? Now, the Grover search algorithm, initially because it did not give exponential speed up, was not paid much attention to, whereas Shor's factoring was paid much attention to because it was affecting cryptography. And it still does. Cryptography is very important nowadays. But search algorithm was important for theoretical computer scientists because many of the NP-complete problems, okay, are essentially search algorithms because you are searching for the correct input to say that to solve the decision problem. Okay? So with the help of this, there are some problems which you can speed up. Okay? So this is all about the flavor of how to do the algorithm design. But now to conclude, building quantum computers and to actually realize quantum computing, you need theoreticians, physicists to build the theory for the systems like photons or superconductors or ion traps, and also to the experimental physicists to actually check whether the theory works. You need theoretical computer scientists to design these algorithms in terms of this sort of models, and you need synthesis methodologies to build large such algorithms and to realize them with whatever technology. So my group at ISI, there's a small group which actually focuses on this part, and the present scenario is that many of the big companies are investing a lot of money. Intel, Microsoft, Google, they are actually working on quantum, have been starting to work on quantum computing to realize large size quantum computers. So the latest here, in fact, the other direction is that quantum communication, and there's an idea of teleportation that without actually physically sending the electron from one end to the other through some kind of optical fiber or through satellite transmission and so on, which has a delay. Quantum teleportation is a much faster way of doing it, and those of you who have found some interest in this area, I would recommend that you read about. So it's a very unique difference again between classical and quantum. And very recently IBM has announced, so 20 qubits means 2 to the 20 states you can use, which gives a lot of quantum computing power. Okay. Now we want to use quantum computer for things that we can do classically fast. We will use quantum computers only for those things which we cannot do classically fast enough. Okay. So we have to keep that in mind, and design. So these are some of the earlier ones. This is the LMR, huge things. But now things have, again, it's become slightly defocused. So the people are getting into, again, solid state quantum chips, okay, some connections over here. This is quantum switches, and this is based on superconductor. So this is a special technology where they claimed it was a 128 qubit chip, but it has some restrictions. So, and as I said before, so these are the polynomially solvable problems. These are the ones which you can solve in polynomial time using quantum computer, but not all difficult problems can be solved. So therefore, my parting remarks would be that there are advantages because it gives significant speed up to a number of problems, but we still have to, and it seems that the disadvantages are to construct those black boxes that I showed, which does things at one step. These are known as oracles. The UF, the control functions out there, and how do you start with the building or initializing, and the implementation of the operators, which is the technology. And last but not the least, that we want reliability. These states have to be kept in isolation. If there is any noise, then the state gets corrupted, so the value gets corrupted. So the computation that you do is error prone. So, and the decoherence, the corruption of the state, is a few milliseconds, sometimes in a few nanoseconds, depending on the technology. So we need what are known as error correcting codes. Okay, so we want to progress towards more reliable and scalable systems, and of course cryptography and communications are very promising, so that's why people are striving to find algorithms using this model. Okay, and there are the physical technology actually emphasizes or rather constrains how to realize them or how to design the algorithms. So there are various future directions, and even multi-valued, that instead of Boolean you could have 3-valued, 4-valued systems where the system's number of qubits becomes smaller, but the computation or realization, the technology behind it is a little bit more complex. Okay, so I'd like to end with this. Okay. So we also need some kind of an operating system. Okay. And this is the famous, shutting his cat, is it dead or alive? So this kind of a thing might happen, but no, of course, it's more of a cartoon. Okay. I'll be happy to answer any questions.
Thank you so much, ma'am, for your wonderful lecture on the topic. I think it's extremely relevant, opening up a plethora of possibilities, and yet quantum mechanics or computer computing is something which we really don't understand much. So it's nice if some of our students and researchers present over here can move forward in that direction. So may I now request our principal ma'am to please come forward and felicitate Professor Susmita Sur Kolay with a small token of appreciation from our end. We are thankful to you, ma'am, for enlightening us and being with us here